All right, guys, are there any questions on any of the homework problems so far? Questions on the homework so far? Homework assignment questions. So if there's no questions on the homework assignments, I believe this is the problem we stopped off on yesterday. Yes. So this is the one I want to pick up with today. So we're skipping one, going to this one here. Write a polynomial function f of least degree that has rational coefficients. A leading coefficient of 1 and the given 0. So this is exactly like what we did yesterday. So they tell us that the zeros are -1 and 4i, which is just really saying that x is equal to -1 and x is equal to 4i, which also means x is equal to -4i. Because our complex conjugate theorem states if x is equal to a plus bi, x is also equal to a minus bi. Or another way to say that is if a plus bi is a solution, a minus bi is a solution. We have to have the positive and negative case of each I. Same thing with radicals. If we have a positive square root of 2, we also have to have a negative square root of 2, or vice versa. Questions on this here?
So wait, what if x is positive 1?
Because that would be a different value than -1. Because we only do it with the I terms, and the main part is going into the fact that a plus bi times our a minus bi. When we multiply this out, because we'd have a squared minus abi plus abi minus b squared I squared. Well, the middle terms cancel. This is going to be -1, which just gives us a squared plus b squared. All the I terms cancel. And that's why we need it. Because when we talk about any of these higher degree polynomial functions, we don't have I as a part of it. Any of the equations that we've had so far, any of the polynomials, we don't have I as a coefficient. And that's because if I does show up, its conjugate shows up as well. Questions on this so far? Now the next thing was to getting these equal to 0, yes? Well, there is a shortcut to doing this because really we're adding and subtracting, yes? We're always doing the opposite of whatever the sign is. So the first one is x equals -1. Well, if I flip the sign, it's what? Plus, yes? I can just flip the sign and move it over. The next one is positive 4i, yes? Because we're just subtracting 4i, yes? So it's just going to be x minus 4i. And what would the last one be? And really, for this one here, it doesn't save that much time. Because really, we could have written it out as -4i, or plus 4i, and plus 4i. And on the other one, +1 and +1. Doesn't save much time. Now, if we think about the one we did the other day, these here, well, the first one, x equals 3 plus I, positive, positive. Well, flip the signs and move. And we go over to the other sign, positive, it's now negative, positive, it's now positive is now negative, negative, it's now just a little bit faster. But we could do it the other way, and here it's just adding 1. Here it's just subtracting 4i, and here we're just adding 4i. We get the same exact thing, it's just a different way to look at it. Any questions on this so far? Now at this point here, we can multiply these together. So we're going to do x plus 1 times x minus 4i times x plus 4i is equal to 0. And again, when we do this multiplication, we always want to multiply the conjugates first. We always want to multiply the two conjugates together first. Now here we're going to have x times x, which is x squared. X times 4i is plus 4xi. Negative 4i times x is negative 4xi. And lastly, negative 4i times 4i is going to be negative 16i squared. When we combine like terms, well, we have x squared. 4xi minus 4xi is 0. Now, what did we say I squared was? Almost, it is negative 1. So what do we really have here? Negative 16 times? It's just positive 16. And last but not least, we need to multiply these two out. X times x squared is x cubed. X times 16 is plus 16x. 1 times x squared is plus x squared, and 1 times 16 is plus. Any questions on this here? Are there any like terms? No, but we'll go on and write it in standard form, which would be x cubed plus x squared plus 16x plus 16 is equal to 0, or we can just say x cubed plus x squared plus 16x plus 16 is our function. Either one works. Questions on this here? Questions on anything we've done so far? Good with this here? Not too bad, just a little tedious at times. Now, most likely, we're going to be able to finish this lesson today, so there's not going to be 3 days of it, because the only other thing we have left is Descartes' rule of signs. René Descartes. That's probably, you most likely do know of him, or at least something that of his work, René Descartes. I think, therefore, the statement, I think, therefore I am. That's René Descartes. He did that also. So philosopher, mathematician. Now, one of the things he came up with is this rule of signs. And what's interesting with the rule of signs is it'll tell us the number of possible positive, negative, and complex numbers that any polynomial function could have. And this is helpful especially if we combine it with the rational zeros in graphs. Because if I know that there's a certain number of positive numbers, it'll tell me how it'll work. Now, the way that this works out seems like it'd be complicated or very overly too many steps, but it's actually pretty simple. For the number of positive zeros of an equation is equal to the number of sign changes of the coefficient of f of x, or is less than it by an even number. So we count the number of sign changes of the function, and then just subtract 2 from it of the number possible. Now the number of negative zeros is going to be the number of coefficient sign changes of f of negative x, or less than it by an even number. And that's it. Now let's go on and look at this, because when we start actually using this, it's going to make a little more sense. So for the positive numbers, we need to count the number of sign changes. And for this here, we just take the normal function. So I'm going to write it out for the first time, for the first one we do. So we have this function here. Yep. So for positive, we just count the number of sign changes. So from x to the 6th to x to the 5th, did the sign change? Because x to the 6th, is it positive or negative? And it goes to? So it does, yes? So that's 1. How about from x to the 5th to x to the 4th? So that's 2. X to the 4th to x to the 3rd. So we have our third sign change. How about from x to the 3rd to x to the 6th? No. How about x squared to x? So how many times did the sign change? So the most positive solutions we could have is 3 or less than it by an even number. Questions on this so far? 2. So it could be 3, or we subtract 2 from it, 1. But if we subtract 2 from 1, we get a negative, so that's it. So if it was, say, 4, well, we could have 4. 2 less than 4 is 2. 2 less than that is 0. So we could have 4, 2, or 0. So with any of the number that we get for the number of sign changes, we keep subtracting 2 from it to see all the different possible combinations. Questions on this so far? Now we're going to look at negative solutions. And for negative solutions, we're taking f of negative x. What that means is every place where there's an x in the function, we're going to replace it with negative x. So which means our function is negative x to the 6th minus 2 times negative x to the 5th plus 3 times negative x to the 4th minus 10 times negative x cubed minus 6 times negative x squared minus 8 times negative x minus 8. Okay. What happens if we multiply a negative number by itself an even number of times? What happens to it? It becomes positive. Anytime we multiply a negative by itself an even number of times, it's positive. So negative 1 squared is just 1, because if we multiply by an even number of times, it always is positive, yes? If we put it to an odd number of times, it is negative, yes? Because if we're looking at the first one here, negative x to the 6th, well, we're just multiplying it by itself 6 times, and the negative is going to become positive, yes? So here, this is just going to stay as x to the 6th. Because the number in front of it is really just negative 1. Let the calculator pull up. So really what we're looking at is negative 1 to the 6th power, which is 1. So we have 1 times x to the 6th. Well, the next power is 5. So negative 1 to the 5th is, because anytime it's an even power, it's going to turn that negative positive. If it's an odd power, it's going to stay negative, yes? And so why that's helpful is because if we look at the next one, well, we know we'll have x to the 5th power. but this sign in here is going to be negative. Negative times negative 2. So really, if the exponent's odd, we're going to change the sign. If the exponent's even, it stays the same. So here, the next power is what? Just 5, 4, even, so the sign stays the same. So it's plus, so it's going to stay plus 3x to the 4th. Next one, our power, is it even or odd? Odd, so it's going to change. So since it was negative, it's now. The next exponent, is it even or odd? It's 2, yes? 2 is even, so the sign stays the same. Next one after it, even or odd? Odd, so the sign will change, but we're also negative 8 times negative x. Negative and negative make a 8x minus 8. Questions on this so far? Count the sign changes. So x to the 6th to x to the 5th, does the sign change? 5th to the 4th. 4th to the 3rd. 3rd to square. So that's first one. Squared to x. So the most odd that we have is 3, yes? Or not odd, most negative we have is 3, yes? Okay. Any questions on what we've done so far? Okay. Now, again, when I started this here, I said this would give us the number positive, negative, and complex. It'd give us all 3, yes? Did the formula or theorem that we had tell us what to do for complex? No, it just said positive and negative, yes? Well, okay. We're going to make a table. So I put it to the side wherever you have space underneath. So, yeah, you can put it underneath. It's not going to take up a whole lot of room. Positive. So I'm using P for positive, N for negative, C for complex. And then I put one over to the side as total. You don't have to do total. I'm going to put it up there. Now, what was the most positive numbers we could have? What was the absolute most number of negatives we can have? What is the number of possible solutions that we have for this function? What's the degree? 6. So the total number of solutions we should have is 6, yes? If I have 3 positive and I have 3 negative, how many solutions do I have? How many should I have? So how many complex would we have? Because I have all 3 positives, I have 3 negatives, that gives me a total of 6. I should have 6, so they're all accounted for, yes? Now we said with this here, because positive or negative, we would have that number of sign changes minus an even number, yes? I always start with the negative amount. Because we could have 2 less than 3, yes? So it could be 3 or it could be 1. I just take 2 away, yes? I keep the positive the same because we want every possible combination of these. Because I could have 3 positive, 3 negative. Or we could have 3 positive and 1 negative, yes? But how many do we have total? It's still 6, yes? If I have 3 positive solutions and 1 negative, how many am I missing? And they would be complex. And again, I would keep taking away 2 away from the negatives. And I take 2 away from the negatives again. Because 1 minus 2 is negative 1. I can't have negative 1 solutions. So what I do with the negatives, I hit pretty much, or as I think of it, I hit the reset. because I put it back to the most that I can have, yes? Because I can't take the negatives down any further, so I reset it back to the total. Which one can I take, reduce? So I take 2 away from the positive, which gives me 1. So if I can do the -2 from the negatives as far as I can, and once I can't do any further, I reset it and take a 2 away from the positives. And guess what we do? Then we do the same thing going back with the negatives again. But we do need to finish this one out because it still needs to have a total of 6, yes? So if I have 1 positive and 3 negatives, that gives me a total of, so I'm missing, okay. Now we do the same thing with negative again. Take 2 away from the 3 and I get 1. So it's possible to have 1 positive, 1 negative, and 1. Because we still need to have a total of. Questions on this here. Can I take 2 more away from the negatives? Can I take 2 more away from the positives? So these here are all the different possible solution sets. Either I graph this and I'm going to have 3 positive, 3 negative. It's going to cross the axis 6 times, 3 positive, 3 negative. That doesn't say that they're rational or irrational, but it's going to cross 6 times. Or it's going to cross 3 on the positive, 1 on the negative. Or 1 on the positive, 3 on the negative. Or 1 and 1. We'll have one of these different setups. And the reason that this is helpful is if I graph this and I see that it crosses twice on the negatives and twice on the positives in our window, which is the only combination that would work? Because if it crosses twice on positive negatives, well, these bottom 3 don't, because all the rest have 1 on negative, positive, yes? So what's the only possible combination I could have? 3 positive and 3 negative, yes? It means that other solution to give me 3 is somewhere out of the range, the window. Because this starts helping me narrow down what are the possible combinations. Because if I see that I have 2 positives, that means these bottom 2 won't work because I need at least, because I have 2, those only have 1. So it's only the top 2. It helps me figure out what possible values, positive or negative, I can possibly have. Does this make sense? And it's nice because it works out this way so where I'm not looking at, especially when we talked about the rational zeros, the first one we did, or one of the first ones we did, it had 32 possible zeros. And especially some of them get more than that. This here limits what I have. Because as soon as I find, say, 3 positive numbers, any other possible positive number is now gone. Because the most I can have is 3. That's why this is nice. That's why the rational zeros is nice. When we start putting these together, it makes solving these a lot easier. We can start eliminating answers faster. Questions on this here? And luckily for this class, you're not going to have to combine all 3 to try to get to the answer. Questions on any of this here? Now, this one here, because on the first one, I think some of y'all wrote it out, some of y'all didn't. That's perfectly fine. Because a lot of times when I do this here, I'm going to look straight at the problem for positives. Because a lot of times I will write straight on the problem, underneath the problem itself, to see the number of sign changes. So from x to the 6th to x to the 5th, does the sign change? Well, yes. From x to the 5th to x to the 4th. X to the 4th to x to the 3rd. X to the 3rd to x squared. X squared to x. X to 9. So we have a total of 3. So the total possible, most positives that we can have is Now for the negative case, we're replacing every x with negative x. And as we know, even powers is going to make it positive, odd powers is going to be negative, especially if we're putting a negative number to that power. Or really for this here, if the power is even, the sign stays the same. If the power is odd, it's going to change. So for our first one, is to the 6th power, it's just going to be 2x to the 6th. Our next one is the 5th power, so the sign will change. So since it was negative, it's now positive. Our next one is even, so the sign will stay the same. Our next one is odd, so it's going to change from positive to negative. Our next one is even, so the sign will stay the same. Now luckily, plus negative x because the power is 1. 1 is odd, minus 9. Yes, they're in the closet, so if you want to go get them, you can. The light's going to be dead ahead. Down the hall on your left. Well, it goes all the way to the wall. So now let's count the number of sign changes. So from the 6th to the 5th power, from the 5th power to the 4th. So that's our first one, from the 4th to the 3rd. 3rd to square. Squared to x, and x to 9. So the most negatives we can have is, so it's just like the last one. Now, most of the time when I set this up, I do positive, negative, complex. I don't put the total. I don't always put that there, because we know the total should be what? 6. So they should add up to 6. So the most positive we can have is 3. Most negative we can have is 3, which gives us a total of 6. So the number of complex is. So then we can move the negatives down to 1, leave the positives at 3. 3 and 1 is 4, which leaves complex at 2. Can't bring the negatives down any further, so we reset them back to 3. But we do reduce the positives by 1. 3 and 1 is 4. We need 6, so we will have and last one we're going to have is 1, 1, and 4, yes? What kind of numbers will the complex be? Well, they'll always be multiples of what? 2. Because our complex conjugate theorem stated if a plus bi is a solution, then a minus bi is a solution. They always come in pairs, always pairs 2s. So for complex, having 1, 3, 5, 7, 9 in that column is never going to happen. All right? So that's one other good way, especially if you're adding these up and you start getting odd numbers in the complex one, go back and look back at the problem, because the complex should always be even. Well, except for 0. 0 is not even or odd. It's just there. Huh? Yeah, it doesn't follow any of the even or odd rules. Because an even number is any number that is a multiple of 2. 0 is not a multiple of anything, and 1's not prime.
So must make the same.
Yes.
Two, like 2 positive, 2 negative, and 2 complex.
Yes. 2 positive, 2 negative, 2 complex. Because the number complex is still 2, not for this one.
Oh.
But it is possible for that to happen. Okay, let's look at this one here. Now for this one here, it's finding the number positive is not too bad. It's just counting the number of sign changes that we have here. So from x to the fourth to x to the third would be, x to the third to x squared would be 2, x squared to x is, and x to 8 is, so the number of possible positive sign changes positive numbers is 4. Luckily I've got space over here. So we know positive is going to start out at 4. Now for our negatives, we're going to have 3 times negative x to the fourth, minus 7 times negative x to the third, plus negative x squared, minus 13 times negative x plus 8. We can't because the calculator needs a value for x. But if the power is even, the signs are going to stay the same because a negative times itself an even number of times is going to be positive. So for 3 times negative x to the fourth, well, we will have x to the fourth, but the negative is going to become positive. It's telling us 3x to the fourth. Sign will stay the same. Now for this here, we are going to have x cubed, but the negative to the third power to an odd power is going to be negative. So it's going to change the sign of the number in front of it. So since it was negative 7, it's now going to be plus 7. The next one's even, so it's going to stay the same. Plus 13x plus 8. Are there any sign changes? So this here is positive, positive. Here, positive, positive. Positive to positive. Positive, positive, and lastly, positive to positive. So the number of negatives that we have is, which here the complex is 0 because the degree is 4.
Can't we just at the beginning?
Exactly. So the number of positives could also be, the negatives is still, and the complex is, can we take 2 more away from the positives? That should be 0 or and. So it could be that this equation has 4 complex solutions. Questions on this here? We can have odd numbers for positive and negatives, but complex, because they always come in pairs, the positive and negative version of I, it has to be an even number. But that's it. Questions on any of this here? That's it. The reason I put 3 days up there is that's what it took last year. It took us 3 days, but there's probably some interruption one of those days that spread it out further. But that's it. That's also the end of chapter 4. Well, a free day from in this hour, technically.